Welcome back. So now we have story time. I'm going to read you a little story. Cambridge University. You don't have to write any of this down and it won't be on the test. Cambridge University, August 1665. There was an outbreak of plague across England that forced the university to shut down. Sound like anything familiar? That's why I'm reading you this. I thought this was hilarious. One of its students, Isaac Newton, returned home. While he was there, he witnessed an apple falling from a nearby tree and asked, "Does the same force that pulls the apple to the ground also pull on other objects like the moon?" This question kickstarts Newton's work on what would later become the law of universal gravitation. But Newton soon encounters a conceptual hurdle: instantaneous speed. You see, gravity continuously accelerates objects, like the apple, and therefore changes the speed from instant to instant. To understand gravity, then, we need a mathematical theory of instantaneous speed, and there was none at this time. So, what did Newton do? He invented one. We're going to follow in Newton's footsteps in this chapter to solve the problem of instantaneous speed. And later, we're going to learn, as he did, that the results can be generalized. And this, ladies and gentlemen, from there, we're going to move on to the tangent line problem. So remember I said that there was two main problems in calculus that had to be overcome. One was instantaneous speed. The other one was the tangent line problem. And you and I are going to solve the instantaneous speed problem together, just as Newton did over several millennia ago. So what we're going to do is we're going to, and this you can write down, so we're going to talk about instantaneous speed discussion. So let's take a look at our apple. So we have a tree, and let's give our tree, I don't know, let's make it a 30-foot tree. I'm just randomly making a tree. And let's have an apple. There's my apple. Look at that. It's even color coordinated. That's awesome. And let's allow the apple to fall for 1 second. And if it's going to fall for 1 second, then we can assume that the time that's elapsed, the elapsed time from when it started to fall from rest, is t equals 1. We call this the elapsed time from start of fall. So the question is, can we calculate the apple's exact speed at the instant that x equals 1? So that's going to be our question. Can we calculate the apple's speed at this exact instant when t equals 1? Well, average speed. Average speed is pretty easy. Average speed is going to be delta d over delta t. And we talk about average speed all the time. Let's say you go to Toronto and you travel 100 kilometers and it takes you 1 hour. Your average speed to go the 100 kilometers over 1 hour is 100 kilometers per hour. Let's say it took you 2 hours. then your average speed, right, you'd take your overall distance and divide by the amount of time that it took. That would be 50 kilometers per hour. So your average speed now is 50 kilometers per hour. It took you 2 hours to get to Toronto. Okay, so that's average speed. And to do average speed, you need 2 points, don't you? You need a starting point, you need an ending point. And that helps you figure out your change in distance, and that helps you figure out your change in time. But at this precise second, there is no passage of time. So at a precise second, there's no passage of time at exactly t equals 1. Therefore, delta t equals 0. And this gives us a big problem. This gives us a very big problem, because then what we have average speed equals the distance over 0. And we're not allowed to divide by 0. This is undefined. And that's where Newton was stumped. That's where Newton was stumped, and there was no math to help him at this point. There was nothing. So, what happened? Well, but calculus is the dynamic mathematics. And what we have up here is static. This is a static system. This is a static way of thinking about things. So calculus is going to be dynamic. So what we had to do was we had to go and talk to Galileo. Now Galileo had already done some work, and he had worked out that any object that falls, any free falling object, has a distance function d of t equals 16t squared. And he worked this out. While Galileo lived, he died around 1650. So this was known for quite a while. And he figured this out with inclined planes. And by the way, for all you physicists out there, they're neglecting air resistance, okay? So this is the distance formula for something falling. So if something falls for 1 second, it moves 16 meters. If something falls for 2 seconds, then it falls for 64 seconds. It's moved 64. And this is in feet. I think I said meters, and it shouldn't have been. It's in feet. So d of t is in feet, and t is in seconds. Okay, so what does this mean? Well, it means, so we knew after 1 second, the apple has traveled d of 1, which equals 16 times 1 squared, which equals 16 feet towards the ground. Okay, let's just stop and recap. Let's see where we are at the moment. Okay, so we have an apple. It's fallen from a tree. We want to know exactly the speed that the apple is going at t equals 1. The problem is average speed requires a change in distance and a change in time. If I'm looking for the speed at a specific time, there's no change in time, is there? That gives me 0. That's a problem. So what did Newton do? He went back and he looked at the work of Galileo, and he said, okay, so if it falls for 1 second, it's going to fall 16 feet towards the ground. We agree? And then Newton said, so okay, what if I let it fall a little bit more? And in a little bit more time. So, and in a little bit more time, say, let's call that little bit more time delta t, it will have traveled d 1 plus delta t which will be 16 1 plus delta t squared. So Newton is allowing it to fall for a little bit longer. Okay, so he's allowing it to fall for 1 second, and then he allows it to fall a little bit farther. Fair enough? Okay. That's the important part here. I'll let my studio audience finish writing this down, and then I'll flip it over, and we'll take a look at what we got. You can speed up the video here. They're still writing. Okay. All right. So let's recap. Tree. Apple. We're going to let it fall. 1 second. We're interested in exactly t equals 1. We want the velocity or the speed at exactly t equals 1. Can't do it. Can't do it. We got a problem. We got average speed is going to be delta d over delta t, and that's going to give you delta d over 0. This is our problem. So what does Newton go and do? He lets it fall a little bit more. He lets it fall a little bit more. Delta t more. He's going to let it fall just a little bit more. Okay? So, remember, Galileo told us that a free-falling object is going to fall according to 16t squared. That's what Galileo told us. So we know when t equals 1, so after the first second, t starts at 0, goes up to 1. We know that the apple has fallen, that's a great word, 16 feet from the tree. So we know that this distance is 16 feet. Now, Newton allows it to fall a little bit more. A little bit longer. So a little bit longer is delta t. So the distance it falls totally is going to be 1 plus delta t. This distance that it falls is going to be 1 plus delta t, which is going to be 16, 1 plus delta t squared. So this is the new distance that it's falling. So the difference between the two distances, the difference in the distances, otherwise known as delta d, is going to equal the second distance, subtract however far it fell in the first distance. So in this case, it's going to be d, 1 plus delta t minus d of 1. So now, if I take a look at the average speed, which is going to be delta D over delta T, we have D 1 plus delta T minus D of 1 over delta T. Depending on how much extra time Newton lets it fall for. He said a little bit of time. We don't know how much that is. That's delta T time. Using Galileo, we can change each one of these into (1 plus delta T squared minus 16 times 1 over top of delta T. Expand the top, we get 1 plus 2 delta T plus delta T squared minus 16 over top of delta T. Expand in the 16, I get 16 plus 32 delta T plus delta T squared minus 16 over top of delta T. The 16 on top and this 16 down here will give me 32 delta T plus 16 delta T squared over delta T. And if you remember, I have a common factoring of delta T here, so I'm going to take it out. I'm going to reduce those delta T's, and guess what I have now? I have an equation for the average speed being 32 plus 16 delta T, which means that we now have an average speed based on the little bit more time that Newton lets it fall. So if he lets it fall a large delta T, he puts a large number in there. And if he lets it fall a small delta T, he puts a small number in there. I can pause the video here and I'll be right back.